Welcome to session 2. Are we all here?
Yeah.
Okay, great. So we'll do another example now. Of course, this one we're gonna obviously I want us to kind of do together. Got two examples to I guess this is one, and then kind of adds on. Okay, I'll just give it a minute and then we can start. People should be on here already.
So
Yes.
So do you know the coordinates already for A, B, and C?
No, you can work it out obviously. Well,
Okay, no, I've tried to figure them out, but I'll wait for you to sort it out because there's just one or two coordinates I'm just not sure, but I'll wait for you to sort out.
okay, cool. Yeah, that's fine. Okay, guys, we're gonna start now. Met these 10, 12 4. So let's first of all, like we said, you want to first get coordinates over here, right? Now, of course, they have identified our planes for us, right? So X, Y, and of course we have Z going up here. So in this case, what's going on here? I think they asked me to sign in or something. Okay, just give me a second. Yeah, but they reset my stuff now. Oh my. What happened there? There, no, yeah. That should be done. Why is it not here anymore? Okay. Nevertheless, yeah, so let's, first things first, let's get our coordinates, right? So we've got, remember, okay, let's look at point A. Obviously, we normally start there. That's going to be -4, right? 0, and that's going to be now. So how do they actually have it? If that's going up, then that's going to be a -7.
That's the one I was not too sure of.
Yeah, because obviously you think like it's going down, it'll be the reason why the way I based, because I'm looking at this force here and I consider that as like a negative Z force. So if this is going up, like at this particular point here, like that's your origin's over there. Then therefore that's going to be like the negative part. So this should be the positive part going up. Yeah. You'll figure it out as you go along. It's a bit confusing sometimes, but you'll see. It all makes sense. Okay, so let's look at B. B would be and I'll give you enough examples to play around with, so don't worry. You're gonna have 7 positive y. That's a positive y up going up, and of course it's all the same, so that's been -7. Okay. Can someone else besides Alex maybe give me C? Guys, please engage. Please, please, please. Mr. Mark, talk to me.
Can I go for it, sir?
Fantastic. Go for it.
Okay, that's a +8.
Beautiful, beautiful.
Yes, and then y, that's positive y, positive 7.
Are you sure? So what is y?
Y is a 3, sir.
Positive or negative?
It's positive, sir, because it's going to the right side. Left side is negative.
Remember, for y, it's up or down, or it's the vertical. So it should be, don't you agree with me, it's -3? Oh, I'm looking at B or C. C, sorry.
Yes, okay, yes, yes, correct, correct.
Yeah, yeah, there we go. And of course, it's going to be -7. Are you all happy with this?
Yes, sir.
Okay, thank you.
Yes, sir.
Yeah, perfect. So now we can just do our first condition of equilibrium. Where's my whiteboard again? It's going to be quick now, guys. Don't worry. So sum of the forces in the x direction. So we go. It's also going to be AD again. Fortunately, same names. So it's minus T A. It's -4. Okay. I'll just first do the x, and you guys can do the y. That's AD. And then B will be, B's over there, so that's 5. So that's positive 5. Whoa, 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 whoa. Oh, this is x, sorry, what am I doing? Yeah. X is 7. 7 TBD. And of course, we have a nice 8 over here. It's plus 8 TACD equals 0. Okay, so we can do sum of the forces in the. Someone can just sort that out for me. This is example in the textbook, but I mean. I'm just sorting out my keys here on my thing. Control C, Control E. Okay, let me just see what works. Beautiful. Okay. Sum of the force in the y direction. Let's get someone else to give me that. Annalisa, maybe.
What are we doing?
The forces in the y direction now.
What am I supposed to do? I'm confused.
No, like setting up the equation.
The matrix.
Yeah, well, yes, the equations or the matrix, if one. Like, so TAD will be 0, TBD, AD. Are you with me now? Like that?
Yeah, and then 5.
Yes.
5
Okay.
BD and minus
Yeah.
3 CD.
Fantastic. Okay, thank you. Yeah.
Plus 5 TB. Yeah.
Plus 5. Oh, that's probably someone's did it. Okay, thank you, Annalisa. Okay, then in the Z direction, they're all normally the same. They all normally should be the same. And so we'd have -7 TAD, -7 TBD, and -7 TCD. But now we have a force there, right? So that was initially negative on that side. And of course, we're carrying it over, and therefore it's a positive. So just be careful of that thing. Don't be like me and make that mistake. Okay, so once you have that, make sure you get a calculator out. Obviously, you guys can do that quickly. And let's see what answers you get. So setting up a matrix, it's going to be -4, 7, and 8, a 0, a 5. -3 is 7, -7, -7, TAD, BD, and CD. That's equal to 0, 0, and 9. Okay. The reminders, are you there? Give me some coefficients when you're done. I'll just use the date one.
Do you want them, sir?
Yeah, go for it. Can you hear me?
Yeah, yeah.
I think
Okay.
just froze. Yeah, go for it.
Tension in an AD is minus 183 over 217, which is basically minus 0.84.
Okay, great. Yeah.
TBD
Yeah.
is minus 0.166.
Great. And CD?
Minus 0.276.
Fantastic. Yeah, 26 or 267. Okay. Let me just quickly see. Okay, my thing's frozen here, so guys, just give me a second to sort this out here. Not exactly sure what happened. Just gonna check what I'm doing here. I might be gone for like a minute or two. Hello. Yeah, it's frozen here. All right, students, I'm somewhat back. Okay, the session is recording, so yeah, it's because my count is set. Really, it's a bit of a mess. But can you guys hear me?
Yeah, I can hear you.
Great. Yeah. I can't even access my bloody whiteboard now. I'm not even sure what's happening. Yeah, I'm opening it now. It just doesn't want to work. Oh, what a mess, man. Okay, it's fine. It's no brain smash. I can all just use Word. Okay, so just keep the PowerPoint open as well. So I'll just share my Word document now. Cool. So my apologies for this, honestly. Guess CPT is not working with me today. Okay, cool. So I think we were busy with the matrix, am I correct? That's where we were.
Yeah, so we just got the coefficients. We just need to put it in the equilibrium equation to find the forces.
Yeah, exactly. So, is there any questions on that? Did everyone manage to obtain those forces? So the forces should be, let me just use another color here. So the tension coefficients should be T, AB, AD. That should be minus 0.8433. We have TBD, and that should be minus 0.1659 or 66. TCD equals minus 0.2765. They all seem like they're all being compressed due to this load. Okay. So of course, first to now find our forces in the members, we have to find the lengths. And if we got our coordinates correct, it was minus 4, it was 0, and it was negative 7. So that is why we find the coordinates as well. It's just easy to find the actual length. So that's going to be let me see. Oh no, it's minus 4. Yeah, okay. So it's just going to be 4 squared plus 0 squared plus 7 squared. Obviously, you have to multiply by the tension coefficient, which is going to be minus 0.8433. What's your force over there? PD. The length in this case is going to be
minus 6.8.
Thank you, Annalisa. Minus 6.8 or 6.8 kilonewtons. Of course, that's a strut. It's been compressed. The next one. The next one is going to be 7 squared plus 5 squared plus 7 squared, right? Of course, we're not worried about the negatives now, and that's going to be 0.1659. That's going to be minus 1.84 kilonewtons. That's also compressive. Then I'll place it right over there, and that's obviously FCD. You should get this coordinate over here. That's 8, negative 3, and of course the negative 7. So 8, 3, and 7. 8 squared plus 3 squared plus 7 squared times, I'm just going to write TCD, and it should be equal to 3,0454 kilonewtons. Do we all get this? Are we all happy with this?
Yeah.
It should be around 12 marks. Yeah, it's not that difficult.
Do you still have to say minus 6.8 kilonewtons, or can you say 6.8 kilonewtons compressive stress?
Yeah, that's what you can say. That's correct. I just had it in my head. You don't need to put signs if you have the the cents in brackets.
Oh, okay.
Yeah, so you can put the cents. I mean, okay, so I have enough space now. Obviously at the end. Yeah. Okay, so I'll extend this problem a bit. So I was going to insert a new page over here. So before we go back to the slides, okay, so let me just quickly go to the slides rather than get back to the problem. So what we're going to do now is check the state of our members. I'm going to play around with some values and see if it's going to fail or not, right? So what I'm going to do is, so I'll just share this quickly. It's all here. Should be able to see it and just confirm. Yeah. So we're going to assume the material what we're dealing with is a spec. It's a standard truss spec. Well, not really, but it's JIS type material. A 16 mil section or plate. And basically, just based on this, we're going to assume it has a yield of 365 megapascals, right? And it has an area of 15 times 10 to the power negative 6 meters squared. Okay, I probably didn't actually put a unit over here. I'll probably just write that again. And what I want to see here is which members will fail, right? This is an extra part which I want to see. So we are considering now that we've grown up a bit normally. I don't know, I think with my previous semester students, we normally consider yield as its failure, not the UTS, because around about at the UTS, the material will actually fracture. So we're going to consider yield as our failure criteria. In this case, it's 365. So my question to you now is, which members will fail? So you have an area of 15 times 10 to the negative 6 meters squared, and we've got a material spec. So how are we going to play around with this? How are we going to do this? So now I just want to revert back to my so-called whiteboard now. And where am I now? Yeah, okay. So you see that? Great. Insert blank page. Okay. Should get the end of this one here. Actually, my cursor is here. Okay, cool. Yeah. Insert blank page. Okay, cool. Yeah. So now, what we want to do is set up some table quickly. I can probably set up a table here inward. Let me just see it like something like that. Okay. We're gonna have member over here. The stress and mode. I'm just gonna call it mode, but we're gonna call it S for structurally sound, if it's okay, or it's gonna be F for failure. So we have member T. What's it? T? It's AG. I don't have to put in the T here, so I can just. AD, BD, and CD. So remember our criteria for this case is where are we now? So our yield is going to be 365 megapascals. That's our yield for material, and I've given you an area, and that's going to be 15 times 10 to the power negative 6 meters squared. Okay. So how are we going to actually see this, if it's going to fail or not? Very simple for this kind of problem. We're just going to use a force over area setup.
Yeah.
Which is a very crude way of doing it, but should be sufficient. So force for the first member, if I'm correct, was around 6.8 kilonewtons. And then we just divide this by 15 times 10 to the negative 6. What answer do we get there? slap and sort out my whiteboard as well.
So you get 453 megapascals.
453 MPa. Beautiful. So we can just call it 453 MPa.
So already
Right.
it's gonna fail that member then.
Beautiful, beautiful. You get the concept. All of this is our extra 6 to 8 marks. Is there a question over there? Oh, it's 365. 365. Yeah, there we go. And then let's look at BD. Can I get someone else to do that for me, please? Some people are very quiet here. Anati, maybe? So in this case, that's going to be now, BD is going to be 1.8. Of course, this is a compressive stress, right? And this we're going to see when we start doing buckling, how I'm going to include the 3D truss, because a member like that won't just fail due to compression. But yeah, you'll see. That's good. And then divided by 15 as well. So we're assuming all the same sizes here. So I'm assuming, of course, it's a smaller value. So it could be within range. Okay, so can someone just please give me the next one? The stress in BD.
122.67.
122.67 MPa. All right, so is that I'll just call it 123. Is that a pass or fail? Is it structurally sound or is it going to fail?
Yeah, so that one is sound.
Yeah, beautiful. Yes, we'll just call it structurally sound. Someone give me CD. CD might be interesting. I'm not exactly sure where that's going to fall in. 3.45 divided by 15. 3 marks, guys. 3 marks.
203,
203, comma what?
comma 3 recurring. So it's megapascals.
Perfect. Yeah, and it's also compressive, and that's well below the yield, and that's going to be structurally sound. So if you apply this 9 kilo, so if I had to ask you as a chief engineer, right, for us to just in a basic form of conversation, how do you avoid, what do you do to make sure that member 80 doesn't fail? There are 2 answers I'm looking for. What did you do to make sure that our whole structure, our 3D trussing remains structurally sound? There are 2 answers which one can actually just answer. Can give really some basic one. Increase the area of what? Can you please be specific?
You can increase the area of member AD.
Yeah, fantastic. Yeah, there we go. Thank you, Zach. And then what's the other thing? What's the last one? Not with I mean, maybe then we shouldn't use a 9 kilonewton load, maybe, right? We can reduce that load, obviously, to maybe 8 or something, or 7 or 5. Maybe our 3D truss is not designed for that particular purpose, depending. So no, those are 2 answers I'm fairly happy with here. So one can, just to understand, one can do this kind of, yes, the way you should approach kind of material analysis or the strength of materials analysis. Okay. Yeah, go for it.
Instead of changing the area, what happens if you change the material itself? Like if it was
Beautiful. Thank you.
Copper, you can change it to steel or something like that.
Yeah, you can say a steel with a higher yield.
Yeah.
Exactly.
Yeah.
It's another one. Yeah. So there's 3 reasons. I really suggest you guys remember those reasons. You might see it somewhere. Fantastic. Really, some good bonus mark questions for understanding there. So please take note of that. Okay. So guys, we're just going to go into the last example now, and I'll just reshare my slides again, and then you guys can go ahead and go practice, go have fun. I think there are a few trusses to solve, around 1, 2, 3, 4, 5, 7 trusses. And if you're able to do that, you should be okay. But of course, always remember the additional questions I always ask. If you always want to know what's happening in your class test assessments, the lectures are the scope. And of course, the textbook obviously shows you, but I mean, focus on the lectures, you'll be more than okay. Yeah, there's some prototype car they've built, and you can see some even when you designing these kind of stuff, there's a truss over there. Obviously, they don't really care much about that, but if their joints are poor, well, that's probably definitely welded up. Just thought a cool picture I found somewhere. Okay, so next is now what happens. This is used when a force is applied at an angle. Right, so we're not getting a force in the X and the Y and the Z directions. What do we do then?
You have to split the force into components, surely.
Yeah, that's exactly great logic there. So what I said they used when force is applied at an angle, not in the direction of points per axis. Obviously, if you have a question like this, you probably get marks for that initial bit. So what does it state here? It's basically using an equivalent tension coefficient, and it says if the externally applied load is not applied in the direction of one of the points per axis, okay, that's literally there, then the components of X, Y, and Z must be calculated. To simplify these calculations, an equivalent tension coefficient is introduced. So what do we basically do? So it's fairly simple. I can actually just work from the slide itself. So let me just move that member up here. Where is this? Okay, cool. So all you have to apply is find this equivalent tension coefficient. I forgot the way bigger TEQ, and that's basically going to be equal to the applied force, right? Which is going to be the one at the angle. So I just want to maybe just copy him here on the side maybe. We have a picture of it there in the corner, and then the applied force divided by the distance between the points, right? So it's essentially the length, it's distance between points. In this case, that should have been point E over here. So distance between points. You'll basically see it's a coordinate. That's AE. And we're just going to actually look at a particular example now of what that actually looks like. Okay, so here's a question. It's kind of stems from that over there. And we've got a truss. We've got 1, 2, 3 members, and they basically show the direction this using the, I guess the stippled line, lines with spaces in between, where that particular the length of that member. So what we basically do is the applied force is 7, and then where they get the 5, 2, and 7, I'll just revert back to the sketch and just increase the font size. Is if you look at E, since someone just give me E's coordinate, that's going to be the whole distance essentially, or AE, or DE in this case. What's the coordinate for that? The X1 is 5. Do you guys agree with me?
I think it's 5 minus 2, and
do I agree with that? Yes. And of course, the whole distance going upwards, which is what?
Which is, what would you say, -7?
Yeah, that's correct. Yeah, I'm happy with -7. That's right. Yeah. So of course, we're working back to there. The final length is exactly the same as before. That Ensa said the distance between 2 points A and E is essentially the length. So we have 7 divided by 5 squared plus 2 squared plus 7 squared. So if you do that, you'll get your equivalent TEQ, right? And are we all happy with that? On how to get the equivalent This is the hardest problem you can get, by the way. Once you get TEQ, you just have to basically find that force in the three directions now. And how we really just do it is you just take, so if you want to find out the force in the x direction, so force in the x direction, this is the one where you make it equal to or not. It's going to be your equivalent tension coefficient, so 7926 times the x coordinate, which is 5 in this case, right? It's important to make sure your sign is right, and if you get that, you get 3,963 kilonewtons. So what this means is that 7 split the x counterpart is going to be 3,963 kilonewtons. The y counterpart, you do exactly the same thing, 7926 times -2. Obviously, that is a negative 2 if you look at the coordinates. That's why I think it's important of getting that. You should get an answer of minus 1.585 kilonewtons. Of course, bring them to the other side, that becomes a positive. And then Fz is just going to be, I think there's a question over there. Yeah, yes, Mr. Royal.
So point E, what can I ask what exactly point E is? Is that just along the line of action for the 7 kilonewtons?
Yeah, I mean, obviously those letters can change, but basically it's the length of that line there. Yeah, it's going from there to there. I can show you another picture. Where is one at an angle? I'm looking at something. Yeah, I'll show you another one now. Just give me a second. Let me just get up to Trotsky here. Another case which looks like that.
The screen isn't changing at the moment.
Yeah, no, I'm still touching my mouse, my graphics tablet here, which is, you'll see it now. I'll copy and paste it now. I'm looking for one at an angle to show you. Yeah, there we go. I was busy on the slide here. Okay, cool. Just gonna say to use this one. What I use? Duplicate. Okay, cool. Yeah, just wanna. Just they call it point AE, but I mean, can you see this one over here? Basically, that force is that 10 kilonewtons at an angle. You see it over there?
Okay, so it's along the line of action for the 10 kilonewtons projected
Yeah,
onto
it's
the
like the length,
thing.
like the invisible length. I don't know what to say. Like it's that length. Yeah.
Okay.
Basically, the force. Exactly. Yeah. It's not
Okay.
point AE. Yeah, it's the hardest this stuff can get. Of course, appreciating the fact for the finding the numbers, and of course then to find Fz, we just take -7. So make sure your coordinates are right, and you're going to times that by your tension coefficient 0.7926, and you should get minus 5.548 kilonewtons. In a case like this, in terms of marks, you get definitely 2 marks for this. So like 1, 2, not that, sorry. I should actually reprogram my key now. No, I don't do that now. Then you get probably 1 mark here, 1 mark here, 1 mark here, or 2 marks depending. Yeah. All right. So once we have that, we go back to our truss and follow the exact same procedure as before. We plot our coordinates. We plot our coordinates for each point. Okay, yeah, we plot our coordinates for each point, and then for now we have these forces, so we have to include the new forces in the actual thing. So can you see that 7 kilonewton is split into that, it's split into this, and split into that. So we don't obviously we don't worry about D and E because we above that. And then You compute, get your matrix, you compute that, and you get your tension coefficients. From the tension coefficients, you can get your lengths. So that's basically all of that in a nutshell. I'll probably post an extra 3 or 4 trusses, maybe 5 if I can find a nice one for you guys to play around with. But of course, attempt all the exercise in the book, then you should be okay. So guys, that brings me to the end of this chapter. Are there any questions I should go over? Or is there any questions regarding the understanding of this?
I think the
Well,
only
those
thing I'm just struggling with, sir, is just like the Z coordinate where you get
Yeah.
negatives. That's the only thing I'm trying to figure out why it is negative. That's the only thing.
Okay, no, it's fine. I get that, but like I said, once you start approaching the examples more, you get a feel for it. Yeah.
Okay.
But roughly, all be roughly explained. Yeah. It's never gonna be like this tricky thing. I don't trip you out for coordinates. I mean, this is a fairly straightforward kind of setup.
All right.
I'll post
And
yeah.
one more thing, if we were to do exercises in this Trotsky book regarding this section, would we start from number 14 onwards?
That is correct. Yeah.
Okay.
That is
Okay.
correct. Yeah. Make sure you attempt all of those.
Okay.
And whatever extra, yeah. Once you know the approaches, really, I mean, guys who have done this before, most students get most marks here. Yeah. But the extra bits, which I like, which I'm going to mention again, is checking when members fail, and also ways to improve the actual design. There will be a new extra bit with buckling, which I always tell them to do something new in the semester, every semester. But yeah. Okay, guys, thank you for taking your time to attend. Really appreciate it. I love having this good amount of students on the live session. Of course, it will be available on recording. Your other students will show you how to do it. Because basically, normally last year I had to post a link for the recording, but the recordings are on Blackboard, but you will get it on there. So next week we'll start on temperature stresses. And yeah, I'll see you for maintenance engineering 2, strength and materials 3 next week. No, not next week, sorry, the week afterwards, because we have Women's Day. So yeah. Okay, guys, cheers for now.
Is that day really important, sir?
Of course it is. It's a castle. Cheers.